Hey everyone, so we're going to go into a little bit more of a deep dive with springs and simple harmonic motion. In particular, we're going to talk about something that we kind of ignored the last time we talked about springs. The last time we actually we mentioned springs, it was in the energy unit, or I should say the first time we talked about springs was in the energy unit. And we talked a lot about the energy within the spring system, but we didn't actually talk about anything dealing with forces. So that's actually what we're going to talk about now. I kind of said in the previous video that as a spring kind of moves back and forth in this harmonic motion, there's a restoring force that's acting on this object. And that restoring force is constantly trying to put the object back to the equilibrium position. And I said in there that the force was called the spring force, F sub x. So I want to talk a little bit more about this. Now, this actually came about from a scientist called Robert Hooke. He designed an experiment where he placed masses on a spring, and he basically saw how long the spring elongated. He did multiple trials because he's a good scientist, and he graphed the data, and he ended up getting this relationship. So he found that pretty much for all springs, that the more force he applied, the longer the spring stretch, and that it followed a fairly linear trend. So once he graphed it, uh, he ended up uh, looking at the variables, and he could come up with an equation that relates the force and the displacement for different springs, right? Um, so because he knew that there was a direct relationship between force and spring, he realized it was a line. He came up with this idea that the slope of that line, which changed depending on what the spring was, the slope must represent what he called the spring constant, represented by the symbol K. The spring constant, as we talked about briefly in the energy unit, is basically a representation of how rigid the spring is. The higher the spring constant, the more rigid the spring is. Now, I can talk a little bit more about it in detail now that we actually are talking about the force. But if you look at the unit, or if you recall the unit for the spring constant was represented in newtons per meter. This basically meant another way of phrasing what the spring constant represents is that it's how much force is required in order to stretch the spring out for a meter. So the reason why we say that a higher spring constant means that the spring is more rigid is that if you have a spring constant of, let's say, 100 newtons per meter, it basically means that every meter you want to stretch the spring, it requires an additional 100 newtons. You stretch it, you apply 100 newtons, it will stretch a meter. You apply an additional 100 newtons, it will stretch an additional meter. Unlike a spring that might have a spring constant of 500 newtons per meter, that 100 newtons per meter does not require as much force. You know, a spring constant of 500 newtons per meter means that it requires 500 newtons to stretch at that same meter. Or if we had a spring that had a spring constant of 1 newton per meter, that basically meant that you had to only apply 1 newton for that to stretch that 1 meter. So the bigger that spring constant, the more rigid and harder it is to stretch the spring, and the more force is required to stretch the spring. So if we look at that, we end up getting this equation for the spring force. Uh, F of x equals kx. Now, you may notice that there's these absolute value bars. Why are they in there? For a few reasons. Again, it goes back to what I mentioned before about the equations represented on the reference table. Uh, x and f of x are vectors. However, they don't point in the same direction. So because they don't point in the same direction, we put these absolute value bars to basically say that this equation holds true for the values of f of x, k, and x, but not necessarily about the vector and dealing with the direction. Now, the weird thing about this, and I'm actually not too sure why they decided to write it like this, because we actually the last time we saw error bars on an equation, it was for the frictional force equation. You know, f of f is less than or equal to the absolute value of mu fn. And the reason they did that was because f of n and f of f are not in the same vector directions. You know, one's horizontal, one would be vertical. So they were always kind of perpendicular to each other, and knowing the direction of f of n did not help us in figuring out the direction of f of f. You know, they again were for the most part independent of each other. However, we actually do know what the direction of f of x will be if we know what the direction of x. So I'm actually not super sure why they wrote the equation like this, because it's more often written like this: f of x equals negative kx. This negative is showing that f of x and x are always going to point in opposite directions, which is kind of the reason why f of x acts as a restoring force. If you stretch a spring to the right, to the right of its equilibrium position, the spring force is going to try to pull it back to the equilibrium position to the left. So it's going to be pointing to the left. If you compress the spring to the left of its equilibrium position, all of a sudden now the force wants to again bring it back to that equilibrium position and push it to the right. So this is actually what the way most people write the equation: f of x equals negative kx. Now, again, I just want to point out something is that just because the equation has a negative does not mean that you have to always incorporate the negative in there. In fact, if you go through my steps on dealing with forces and you do your whole FBD and you kind of do some of the forces using that FBD, you won't have to worry about the negative in this equation, because doing the FBD already takes that into account, right? If you draw an FBD and you draw the direction of each of the forces appropriately, then when you do some of the forces and your F net equation, you're looking at your FBD to come up with what terms are positive and what terms are negative. So you're not using the negative in this equation. So I just wanted to point that out there, that we do know the direction of x and fx, their relationship. However, like I said, you're not going to worry about it too much. This is more useful at college level physics when you start dealing with these problems in uh, cardinal direction vector notation. The negative then ends up working a lot better. Or if you're dealing with calculus, it can be better to kind of keep that negative in there. But like I said, you don't have to worry about it, right? So this is actually just a visual representation of what I was referring to before about how the position x and the force are always in opposite directions. See, you can see that as the object's on the right hand side, the force always pushes to the left. When the object's on the left hand side, the force pushes to the right. So they're always going to be in opposite directions. Now, one thing that I want to point out is that the uh, relationship that I showed you before, the direct relationship between force and the spring stretch being linear, was only true up to a point. I'm sure everyone has this scenario that they've done before where they've played with a slinky and then they've stretched it too much and it's gotten destroyed. My son's actually done that. We bought him a slinky, and pretty much 2 days later, the slinky was completely ruined and no longer acted as a slinky. Well, what's going on there? What ends up happening is that springs end up they end up having this direct relationship and returning back to their normal conditions in what we call the elastic region. In this area, the spring always returns back to its original condition and position, and everything's hunky dory. But once we reach this specific point called the elastic limit, and we continue to stretch the spring, it enters into a new region called the plastic region. And when it enters into this plastic region, the spring immediately gets permanently deformed, and it never goes back to its original situation and condition. So if you've ever overstretched a slinky, it's because you've had the slinky enter into that plastic region, and now it's completely deformed. And if you continue to stretch it, eventually it would end up breaking. So just keeping that in mind, that the whole direct relationship between force and elongation technically only lasts for a set uh, distance or set length for that spring. Each spring is different and unique, so we can't really determine that. But it's just important to know that there is a limit to how much we can stretch it and have it return back to that original condition. So here are some practice problems. Pause the video, work self, and we'll go over in a second. All right, so we have this spring. It's being hung vertically, and they give us this stretching distance. So they want us to figure out what the value of the spring constant is. So we just use the equation. Again, I don't need to worry about the negative, so I'm just dropping it, you know, because it really doesn't matter. We're just looking for the value. We plug in the numbers, making sure that we convert. I didn't want to say convert. We use this mass to calculate what the weight is as 2.5, and we end up getting 50 newtons per meter. All right. Make sure that your units are in the proper set. Like if this was in centimeters, which they do love to do, that you convert it into meters. All right, here's the next one. Pause video, works up, and we'll go in a second. All right, here they give us the weight is 20 newtons. However, they don't explicitly tell us what the stretch is. Remember, the X does not represent the length of the spring. It represents the change in the length of the spring. So the spring went from being zero point 0.5 meters to 1 meter. So X would be 0.5 meters. Plugging that in, we end up getting 40 newtons per meter. And that's pretty much it. There's what we're going to talk about in class is about the energy within a spring system. So yeah, if you have any questions, feel free to let me know. Otherwise, good luck and have a great day.